Hey, I guess you're pretty proud at doing differential calculus, and so you should be. And I've got something interesting here for you. It's called the derivative and curve shape up the top here. And what we're going to do is try to understand why the graph may be a curved line. I wonder if you've got any ideas about that. What about this red hot question here? Why might the derivative be important? Any ideas? Curves. Oh, curves. What's the difference between a curve and a straight line? Okay, what makes a curve curvy? Well, why is it different from a straight line? Well, let's have a look at a straight line again. Remember, we said delta y, or the y step over the x step, between any 2 points on a straight line is the same, isn't it? It's a constant slope. Slope is y step over x step, changing y over changing x, and that is constant for a straight line. Hey, for a curve, would it be constant? Let's look at this dude over here. Hey, as we go along the x-axis here, coming along, we usually would start to the left, and as x increases, what is happening to the function? Oh, it's going down, it's decreasing, and it's decreasing at a changing rate, isn't it? It's steeper up the top, less steep down the bottom. Hey, I think that's what the derivative can measure, can't it? Remember, the derivative measures the slope of the tangent. Let's draw them in. There's some tangents here. Getting less steep. Actually, the slope of that one there would be 0, wouldn't it? The horizontal line slope is 0. So we can track the behavior of a function or a curve by the slope of the tangent or the instantaneous rate of change. You know, they are synonymous. They mean the same thing. And so we can track what's happening. And look, it's increasing here. Look, the steepness of the tangent is changing, getting steeper. Hey, that's what makes a curve a curve. Hey, and the derivative is important because we can track how fast that is changing. Hey, this is pretty powerful stuff now to actually understand why a curve behaves like it does. And here's a graph of x cubed down here. This is interesting enough. It's got an interesting flattening point. Don't know whether you've seen x cubed much. You can follow that on your graphics display calculator and see what it's like. And then, of course, some ordinary polynomial functions. I haven't done a lot of these. Maybe just you're used to quadratics like the one at the top there. But here's what's called a cubic function, x cubed in it. And it's got some turning around points. And look, we've got some tangents drawn there. Hey, we might be able to determine, actually, in higher powered functions, polynomials, where their turning around points are. Because that would be where the tangents are flat. Just producing tangents parallel to the x-axis, and the slope is 0. Did you think of that when we first started drawing tangents? I guess not. But gee, it's powerful stuff, isn't it? And this is going to be very interesting for you, this presentation. So let's go down and let's pull some of those ideas together. And here's the first one. Let's just look at the old quadratic here. F of x equals x squared. You know it plots like this. It's a parabola. You remember where the word parabola comes from? The Greek word thrown? Because, when you throw something, it goes like that. So a concave down parabola is actually the shape of an object which is shape of the path of an object which has been thrown due to gravity and so on. So that's interesting, isn't it? Parabola. Okay. All right. So x squared, f of x equals x squared. We have a derivative from the last presentation, which is 2x, the x to the n rule. Remember that one. If f of x equals x to the n, the derivative is nx n minus 1. And we just use that there to get 2x. Now, let's do a sign diagram. What's that? Oh, remember what I said? We're going to track the behavior of the tangents, track the tangents to this curve. And how are we going to do that? Track the tangents. We're going to track the value of the derivative. Okay, so let's find when it equals naught. Hey, what's that? That's a flattening point. Come over here to this diagram, and can you see that we're going to make that an important point, because that's where the tangent has a slope of 0. So let's put the derivative equal to 0. And if we do, when is 2x equal to 0? When x is 0. And we're going to track the behaviour of this curve on either side of that flattening point. So let's sub in values from in here. Well, let's sub in neg1 maybe. Let's go back up there actually. So let's sub in neg1. If you sub in neg1 in here, you get neg2. So over on this side, the slope of the tangent is negative. They're all negative values. And all the way it will be. All the way back here they'll be negative. Why? Because it won't change to a positive unless it goes through a 0 position, will it? Function changes sign above or below the axis by going through a 0 position in these little polynomial functions, that is. It is possible in rational functions to change sign without going through the 0 position. Okay, what about over on this side? Let's sub in a value of 1 in here. And 1 into 2x gives us 2. It's positive on this side. So what have we got? Would you like to draw a little map here? The slopes on this side are negative. Negative lines come down like that. Then there's a flattening. Then they are positive. So you've got a little graph, a little track of the shape of the graph, because the tangents over here are negative, tangents over here are positive, and in the middle you have a flattening. Hey, we've almost tracked it out without plotting any points. Okay, so what can we say? F of x is x squared is decreasing over on this side. Let's have a look at that tangent coming down. Tangents are negative. So over on the left-hand side, x is less than or equal to naught. The tangents are negative. The function is decreasing. Okay, let's check it over here with the graph. Over on this side, we said all the tangents are coming down like that. Please note, we always talk about a function in relation to x increasing. Otherwise, it gets confusing. Okay, we always think about x increasing along the x-axis and discuss what's happening to the function always relative to that movement in x. Okay, so I don't actually like that arrow there. I like to think of as we move along the x-axis, x increasing, what is the function doing? In this region, function is decreasing because its tangents have a negative slope, and on the other side, as we x increases, the tangents are increasing here, becoming more positive. And gee, that's what's happening when we come back over to the graph, isn't it? Oh, how powerful is this derivative now? How powerful is it in giving us an idea of the shape of a graph with no calculator? Hey, we're getting into some good maths here. Okay, let's go and look at another one. We had a glimpse of this a minute ago. So here's the concave parabola, okay, opening downwards or whatever. It's neg x squared. So let's do that. Its derivative is neg 2x. Put the derivative equal to naught. We're getting some steps here now. So that is when x is naught. So we're going to find our flattening point. Okay, when the derivative is naught, means the tangent is horizontal, has a slope of naught parallel to the x-axis. Sub in a value from this region. Let's sub in neg 1 in here. Neg 2 times neg 1 is positive. And over here, if we subbed in plus 1, neg 2 times plus 1 is negative. So what's happening? We have positive slopes. Positive slopes go that way on the Cartesian plane. There's a flattening and then there's a negative slope. Okay, so what's happening there? As we go along the number line here, so this sign diagram is really just a bit of the number line, isn't it, of the x-axis. As x increases here, what's happening? On this side, f dash x is positive. Okay, so the function is increasing. On this side, it's less than naught, it's decreasing. And you might like to think of this also, not just in terms of tangents, but the derivative is the rate of the change, rate of change of the function, rate of change of f of x. And if it's positive, it's got a positive rate of change, it means as x increases, the function increases. So that's another way of thinking about this increasing and decreasing. The rate of change idea, which is the same as, implies the slope of the tangent. There's that dichotomy there, the slope of the tangent. Okay, two ways of thinking about it. Please remember Huddy's favourite diagram here in calculus, differential calculus land, and that's this one. The derivative means the slope of the tangent, looking at Newton's idea, coming at it from that point of view, or the instantaneous rate of change of the function. Okay, all of those. Around the circle we go. When you talk about the derivative, I want you to think of both of those consequences, if you like. I mean the same thing, but slightly different ways. And Leibniz was focused here very much on rates of change there. Well, they both were, but we've got slightly different emphases. All right, so what do you think? We're getting somewhere here, aren't we, with tracking this function, understanding when it's going up, when it's going down. Okay, let's do some more to get the hang of this. And I want to add something to this here now. We just come down here a little. Oops, hang on too much here. Okay, so just come here. Okay, so I'd like you to put here SD, sign diagram, for f dash x. I think labelling that is always a good idea in problems. These screen clippings here particularly come from a publication by Hayes and Harris. Okay, so thank them for that. Here, x cubed. We've said the graph looks like this, and it's got this interesting flattening point there. Let's see if we can track that behaviour without knowing this, without a calculator. So let's get the derivative. It's 3x squared. We'll put it equal to 0, and we find that x equals 0. Actually, two solutions there, isn't it? X squared is 0 means x by x is 0, so x is 0 twice actually, two solutions. So when you have x is 0 there, if you sub in neg 1 from here, let's say, neg 1 squared is 1 times 3, that's positive. Or 1 subbed in is positive. Uh-oh, it doesn't change sign. Have we done it? Yes. It's positive slopes, flattening, positive slopes, and that's exactly what this function is doing. So that means as we go along the x-axis here, x increases, the function is going to increase, then it's going to be flat, tangent's going to be horizontal, parallel to the x-axis, slope is 0, all those old things, and so we've tracked it. So it's actually increasing for all x, always going up those tangents. Or f dash x is always positive, always greater than 0, which implies f of x is increasing purely from the derivative, because f dash x measures the rate of change of f of x, and it's always positive, always increasing. Getting the hang of it. It's powerful stuff, isn't it? That you can come at these graphs never having seen them before and without a calculator. Let's summarise some things here, and by looking at this particular example over here. A cubic, now you've never studied these usually by this stage in one's course now. You haven't studied polynomials. Polynomials, what are they? Well, the simplest polynomial, of course, is a quadratic. Okay, we've got something like y equals ax squared plus bx plus c. Poly means many numbers or many powers here. So you've got a squared power, a single power of x, and x to the naught here, if you like. So there are many powers of the variable here in this polynomial. That's the simplest polynomial. Next one up is called a cubic, because it starts with, or its leading term or highest power or degree is 3. There's no x squared term in this one, and there's x, and then there's no x. So this is a polynomial with the highest power or its degree is 3. So they often look like this, a pretty characteristic shape. But let's say we don't know that. Can we find it out? Come over here. Let's get the derivative. Derivative of x cubed, 3x squared, derivative of neg 3x, neg 3, derivative of the constant 4 is 0. So let's put this equal to naught. There we have factorised it, put equal to naught. You get x is either x plus 1 is naught, which is x is neg 1, or x take 1 is naught, x is plus 1. Okay, or you could have done it like this. This is acceptable as well. Okay, dividing by 3. So x is plus or minus 1. Okay, could do it that way. So on our sign diagram for the derivative, we have 2 0 positions for the slope of the tangent, or for the derivative, neg 1 and 1. Let's sub in from this side. Sub in, let's say, neg 2 back in the function, and you'll get a positive. Sub in something from in this region, sub in 0, you'll get neg 3, that'll be a negative. Sub in 2 from here, you'll get a positive. So these are the signs of the slope of the tangent, if you wish, or the derivative in those regions. So it's going to go what? Positive, 0, negative. And in this region, negative, 0, positive. Remember those signs on the Cartesian plane. Remember, if we say something has a positive slope, we're going like this. That's a positive slope. And if it's got a negative slope, it goes like that. So that's what we're trying to track. Trying to track the behaviour. Have we got it? Yes, look at it in there. That's very much what the graph looks like. Positive, flattening, negative, positive. Okay, we have got a tracking device. I think we've made it. We can track the slopes, the changing slopes of this function without a calculator. Okay, so here's the definition. If we have an interval of real numbers, so that's saying we're going from one x value to another, and let's say if we want to find out where the function is increasing, that means its derivative is greater than or equal to naught. If it's decreasing, its derivative is less than or equal to naught. Okay, can you see any problems with that? There is something wrong or something a little bit confusing about that. Well, actually, can you see it in here? We're actually including 0 position as a point of increasing nature for the function and decreasing. How can it be both? Well, the boundary, so here they are here, these boundary positions. So in this region coming along to here, f dash x is greater than naught, and then it equals naught, f dash x equals naught, and then it's decreasing here, it's coming down, isn't it? We include the boundary in both intervals. So we say it's increasing right up to and including this 0 position, then it's decreasing from there up to and including this next position. Okay, so we include the boundary. So right here on these positions, it isn't actually increasing or decreasing, isn't it? It's 0. So it's actually stationary, if you like. The function is actually not technically changing at these points here. Okay, it's not greater than naught, it's not less than naught, but we do usually include it in both. And if you don't like that, if you want to be more strict, we can call it strictly increasing. This is how we do it in maths. Strictly increasing means f dash x must be strictly greater than naught, don't include the boundary. And strictly decreasing means f dash x is strictly less than naught. Don't include that boundary position where it flattens, which is technically, come over here again, it's a stationary point, isn't it? The function isn't increasing or decreasing there. Its derivative, its rate of change measure, is 0. Interesting enough, just so getting some technicalities in here. Make sure there's no confusion. Okay, come on down. And let's look at some examples again. I've taken these from Hayes and Harris, got a good set of examples here. So find the intervals where the following functions are increasing or decreasing, and here's our 2 functions. Okay, let's do the first one. You state the function, get the derivative of neg x cubed, neg 3x squared. Derivative of 3x squared, 6x. Okay, we can then factorise that and put it equal to 0. They're not showing this, so x would be 2 or x would be 0. Putting those two equal to 0. Let's just check it. Here, null factor law. The product of two factors is 0 if one of the two factors is themselves null or 0. So here we have it here. X is 2. Just remembering that from quadratics. Okay, so we have a sign diagram. Let's draw some tangents in. Negative, flattening, positive. Positive, flattening, negative. Okay. Oh, that agrees nicely with that. Okay, the idea, and I'd like to label this sign diagram for f dash x. So can you see it? To the left here, f dash x is negative, so it's decreasing for x is less than or equal to 0, and also over in this region it's negative, so it's decreasing for x greater than or equal to 2, and in the middle between the two it's increasing. Got positive slopes in there, and you can check it on your calculator and have a look. Okay, let's look at the other function. 3x to the fourth take 8x cubed plus 2. Let's get the derivative of this one will be 12x cubed, x to the n rule, take 24x squared, derivative of a constant is 0. So then factorising that, the common factor is 12x squared. In here you multiply by x, take 2 to get our two terms. Okay, and then putting it equal to 0, you'll have x is 2 or x is 0. Okay, so again, sign diagram for the derivative. And what are we going to do? Let's go to 0. Let's plug in a value here of neg 1. Put it back into our function, our derivative function there. Find its negative. Put in a value of 1 in here into our derivative function, and then 3. And what we find now this time is, it didn't change sign. So negative slope, flattening, negative, and then in this region negative, flattening, positive. And yes, that's the sort of graph we would expect to be seeing. But what we're interested in here is stating whether it's decreasing or increasing. It's decreasing when the derivative is negative. So right through this region, anywhere less than 2, it's decreasing, and once it hits 2, it's increasing. And you can see that through here. As x increases, remember we always go this way, as x increases, the function's coming down. As x increases here, the function goes up. So it's decreasing less than 2, increasing greater than 2. And we include the boundary condition of equals 2, as long as they don't ask us strictly increasing. Okay, let's go down and do some problems and see what you think. So here's a little set. Probably we wouldn't do all of these. Probably A is a bit easy. They might do B and some alternate parts, do some of the polynomials. Maybe a function like that you're not familiar with. Certainly one like this and this. Maybe the root one there. A couple of others, get the hang of it. Okay, you may not have time to do all of them. The ideal thing would be, of course, to do all of them. And, of course, you can check along the way with your graphics display calculator. Just remembering, though, this could be in paper 1 and you won't have that calculator on board there. Okay, let's go down and have a look at the solutions. Have a go at some of these and scroll forward and back. As you do one, check it so make sure you're on track. So let's look at those solutions then. Okay, so here is a bundle of them down to F. Okay, sign diagram, not a bad idea. Well, they've put it up there, the title for the sign diagram. Put it alongside the actual little piece of the x-axis. Just remember, this is really thinking about a little piece of the x-axis, isn't it? And travelling along it. Okay, so let's have a look at some of the others now. GHIJ, and then KL at the end there. Okay, so scroll forward and back as you do your work. and check your answers. Let's go on and see if we can put some more of this together. I think you have seen what I've said already. A stationary point, and what we were saying was a stationary point is one where the function technically isn't changing. So its rate of change measure, the derivative, would be 0, or the tangent, doing that one, would be flat, parallel to the x-axis, or horizontal if you like. So I guess you didn't realise how important that tangent being 0 really was, because it means no matter how complicated the function, we can find the stationary points or the flattening points. Just remember they are turning points there, but stationary points, as with x cubed, may not be turning points. We'll talk about this one later. That's a flattening of the curve there, but it doesn't turn around. Okay, so a stationary point is where the derivative is 0, because technically the function is stationary, it's not increasing or decreasing. F dash x is 0, even though we include that boundary in the increasing and decreasing values. Right at that point, the derivative is 0, the function is therefore not changing. So it could be a local maximum, local minimum, or stationary point of inflection. Inflection we'll talk about later. So it's just inflecting, isn't it? It looks like it's going to go down, concave down, but then it goes concave up. So it's just an inflection of a little point there where there's a bit of a change. Okay, but just keep in mind also that the function goes on here in this case. So it's only local. That's a local maximum. See, if we keep going here, that will beat it. And over here there's only a local minimum. If we keep going down here, we will beat it. So it depends upon the domain that we're going to consider as to whether this is actually going to be a maximum for the function. So it's only a local or relative. I think Pearson, we were talking about later, used the word relative max or relative min, relative to the points in that particular part of the domain, not forgetting that we can go up and down here and beat it, go past those values. Okay, let's get some of this language together now, because we're en route to trying to draw the whole graph. Okay, so let's consider this graph from -5 to 6. So stopping here at x is -5 and x is 6. Okay, what are we going to do? Let's do some definitions here. A is a global minimum. Global meaning on that entire domain, in that part of the world, or the globe if you like, then this is as low as the function gets. And B up here is a local maximum, because it is exceeded by D later on. Okay, and you can see f dash x is 0. Okay, at that point, a flattening of the tangent of the curve. And then C is a local minimum, alright, because the derivative is 0. And then D is a global maximum. Global meaning within that definition of the world or the domain, on that whole domain. Okay. Now, this is an important point here. A local maximum or minimum could be the global maximum or minimum. That could be all that you have there if we restricted the domain, except so if we stopped it there and there, then that would both be the local max, local min, and global, if we didn't allow the function to go higher or lower here. Okay. Alright, so here y equals x squared. Let's draw that one. Y equals x squared. There it is. And that is this local minimum can be exceeded here. Sorry, you can get bigger values, but you can't get less values here. So it's both the local minimum and the global minimum, as you can't get less than that with x squared. There's just some terminology there that we're looking at as we go on. But we're talking about turning points, maximum, minimum values now, and let's have a look at using that idea. Okay, so here's the other stationary point I mentioned just above there. you can get a flattening like this. We call that a point of inflection. Okay, so when the derivative is 0, we have to check the signs on either side, because here's x cubed, we've done this, 3x squared, derivative is 0 when x is 0, and if we drew a sign diagram for the derivative, thinking we don't know the graph, let's forget that, sign diagram for f dash x, stick in neg 1, it would be positive in here, stick in 1, it would stay positive, which means it's coming up, flattening and going on. So that's the idea here. Okay, so the tangent here is horizontal, but it's neither a local maximum nor a local minimum. It's called a stationary point of inflection. You can use an X in there if you like. As the curve changes its curvature or shape, what do they mean? Well, it's coming up here, look at this. The slope of the tangents is decreasing, still an increasing function because they're positive, but it's getting flatter. Then instead of going around there, because this is like a cave here, isn't it? Concave down there, that looks like a cave, but then it plays funny, and it goes, the slopes of the tangents are up like this, which is like concave up, or convex. So can you see, at this flattening point, it does change from a cave shape down to a cave shape up. So this is called a change in curvature. So a point of inflection is a point where it does change curvature. And what's happening with the tangents? Well, in here they are getting very flat, and then up here they're increasing. So this is actually the lowest value here of the tangent coming in there. They're decreasing and then increasing. So we'll come across that later on, looking at that change in curvature. Okay, trying to pick that up. That's called a stationary point of inflection, because we do have that change in curvature. All right, let's go on. Bit of language coming up now. Stay with it. Okay, sign diagrams. Here's the graph. The sign diagram of the function of the gradient derivative, so I'd like to put here sign diagram for f dash x, is underneath it. Let's have a look. Neg 2 is a flattening point, yes, and 1 is a flattening point, and 3 is a flattening point. So these are the values that go on our little bit of the x-axis, our sign diagram, because they're the zeros. Subbing in each of the regions, we would get this sign diagram, and we can map it. Positive, flattening, negative. Negative, flattening, positive. Positive, flattening, positive. Okay, so something like that would be our sign diagram, and it would give us a very good idea that the graph looks like this. Okay, so that's what we've been doing, basing it all on the 0 positions for the derivative, which are called our stationary points. Okay, stationary points. They're not all maximum, minimum or turning points, because you can get one of these in here. So when we talk about the whole group, we call them our stationary points. Stationary because the slope of the tangent is 0, but hang on, this derivative means the rate of change of the function, and so it means the function isn't changing. That's why we get the word stationary in there. Okay, let's have a look at a bit of a summary. First of all of these can be detected by calling them stationary points by finding when the derivative is 0. Okay, so if the sign diagram around that point, if you find the x value to make the function 0, sign diagram, a little bit of the x-axis, and we travel along the x-axis here, we find it's positive and negative, that's going to look like that. Positive slopes, flattening, negative. Okay, got the idea? This is a summary of what we've just been doing. Local minimum is going to be negative, flattening, positive. That's going to look like that. And then the stationary inflections, positive on either side means like that, negative, flattening, negative, so there we have it. Gee, we have a good detecting mechanism now, haven't we, with the derivative. We can really find what this function is doing, and we can see why it's doing it. Okay, let's do some more examples here. And here we have a function. Now we're going to draw the whole thing, not just find when it's increasing or decreasing. So we'll get its derivative term by term, factorise it twice here, put the function equal to naught. I'd like you to show that. So the x take 3 is naught, or x plus 1 is naught, null factor law, so x is 3, or x is neg 1. Okay, so here we go, 3 or neg 1. Sub in a value from here, let's sub in neg 2, back in the derivative, trying to find slope of the tangent, becomes a positive. Sub in 0 in here, it's negative. Sub in 4, it's positive. So what do we got? Positive, flattening, negative. Negative, flattening, positive. So we have a local minimum. Oh, hang on, I just did all that incorrectly, didn't I? Positive, slope. Okay, no, that's okay. Positive, flattening, negative, negative, flattening, positive. Okay, have a local minimum at x is neg 1. Local maximum, sorry, that's it. At x is neg 1. Very good, sub it in is 10. Local minimum of x is 3. Sub it in. Okay, very good. I was misreading that down below there. Okay, so we have the neg 1, 10 is the max. Neg 1, 3, neg 22 is the min. We're getting these values by subbing in, not in the derivative, but into the function. Right, just remembering when we have a function y equals f of x, if we sub x in here, a particular x value, we get the y value to go with it. So this is the y value of the point. So that's what we're doing there, actually finding out where it is so we can actually plot it. And we'll get something like this. Obviously, graphics calculator, if it's in paper 2 in the IB, will help you a lot, but we've got to be able to do it without that. So let's have a look now at what would you do. So here's the Casio, this is the TI up here. So the Casio, graph a function, this is in graph mode. Okay, graph the function, and then hit Shift F5, okay, which is Gsolve in there, can't read that very well. Gsolve, that comes this window, and here it is, you can find the max and the min. Okay, and other things as well. So if you hit F2, the crosshairs sit on there and it reads off what that value is, okay, for any function there. Okay, so that's our neg 1 value there. Alright, so let's have a look then at doing some more with these. Here we are. Find and classify all stationary points of this one. Okay, first step, get the derivative to track it, factorise it, common factor of 4x squared. What do you multiply 4x squared by to get 4x cubed? It's x. What do you multiply 4x squared by to get neg 12x? It's neg 3. Then we put this equal to naught. I like to show this. Naught and x take 3 is naught. So x is equal to naught. This is twice. This is repeated, because this is x by x equals naught, and x equals 3. So you'll see an interesting result of that here. Put naught and 3 on the sign diagram, sub in neg 1 into the derivative, because this is a sign diagram for f dashed x, and you get 0, get negative, sorry. In here, sub in 1, you get negative. You notice because this is a repeated 0 for the derivative, there's no sign change, because this was a repeated 0 for that function. And then here, sub in from this region 4, and you get a positive. So what have you got? Negative, flattening, negative, and then negative, flattening, positive. Okay, so that agrees with this graph up here, and you can draw it. You need to plot the actual points, of course. So when x is naught, sub it back right into the original function there. So you got the point naught to neg 2. When x is 3, sub it back into the function, get the point 3 neg 29. checking on the calculator if you're lucky enough to be able to use one. In paper one, just remembering you can't. Okay, so let's do some. Alright, so here's a bundle here. I think you can do the first one as a bit of a summary of what we've been doing. Question 2, again, it's some of the same functions from before. Just try a bundle of those. You're probably up here we'll try some of the polynomial ones, some of the square root ones. Okay, and just check that you're pretty familiar with that. Okay, and then there are some answers coming up down below here in a minute, so I'll get you to pause the presentation and have a go. I'll toggle forward and back, but let's have a look at some of these other questions here as well. 3, what value of x does a quadratic function have a stationary point? Using calculus, okay, you've got a stationary point, there's a turning point, and there's various other ways of finding with a quadratic function that turning point. You'd know this at this stage. Well, we want to use calculus here. Okay, and what conditions a stationary point, a local maximum, a local minimum? That's a bit of an extension question. And here's another one. Find the values a and b in here if it's got that stationary point. So stationary point, remember, means f dash x is 0. So you have to go through the process there and see if you can backtrack for the two unknowns a and b. You might keep in mind, if you've got two unknowns, you'll need two equations to solve for two unknowns. So that'll give you one. I wonder if you can see, using the point, how to get the other one, using the ordinary function perhaps. Okay, what about this one here? Cubic polynomial touches the line with equation that. So can you find, that's a tangent then, isn't it? Okay, so if you can find the slope of that line, you'll have the slope of the tangent. Maybe you'll be able to create some equations there. Okay, see what you think. That's a pretty hard problem, that one. Okay, so have a go back, start, have a go, and let's go on then to the solutions to those 5 problems. These are from Hayes and Harris again. So there's on the first ones, question 2, A and B. Let's go down to C and D. I'll just come up a little bit there. C and D. Okay, and then E and F. Just noticing the notation here. I would generally suggest we do that, meaning the function is undefined on that side because of this square root of naught, which will occur, or square root of negative, which will occur right down that way. So you can use that hashing or just showing this here that's undefined. Okay, let's do G and H. Okay. And I and J. And some of the trickier pieces here. Question 3 and 4. And question 5. Okay, did you get the idea there that you needed a general polynomial, general cubic, ax cubed plus bx squared plus cx plus d? Harder question, that one. Okay, how are you going? Might have to go back and check through some of this again and take it in smaller pieces. I'm going to go on now. Let's have a look at this idea of points of inflection. And we've mentioned this already. It's a change in curvature, isn't it? We said a point of inflection was a change in curvature, where the curviness changed from down to up. So this is concave, or concave down. This is concave up, or sometimes called convex. In the IB course, they're going to use concave down and concave up. Okay, concave up, concave down. Okay, here we are, summarised nicely there. So we're looking at how we can detect when it's going to change around from downwards to upwards. Let's see if we can get that detail now. So the test for shape, here we are. Okay. If you've got a concave downwards curve, here we are, what's happening? The slope is a positive, less positive, 0, and then going to a negative. So the values of the derivative, here, the values of the derivative are actually decreasing. But these values of the derivative are actually decreasing here as we go through that position and down to here, because we've got positive values for the tangent, slope going to negative for the slope of the tangent. So that is said to be a decreasing situation when values for anything are positive going to negative along a number line. That's decreasing, isn't it? So the function is getting more and more negative. It's said to be, derivative, sorry, is getting more and more negative. So it's said to be decreasing. So as x increases along the x-axis coming this way, x increasing, the actual value of the slopes going from positive to negative, they are said to be decreasing. Oh, that's interesting. That characterises concave down. Let's look at concave up. The tangents here, we've drawn some, are going from negatives through to positives. This is said to be when something's going from negative values here through to positive values as x increases. They are said to be increasing value, because as we go along the x-axis always to the right, as x increases, the gradient of the tangent is increasing. Therefore, f dash x is increasing. Well, that's interesting, okay, because that's going to allow us to determine whether it's up or down in a different way and where it's going to actually change. So let's have a look now at that idea. How can we show that any function is increasing or decreasing? Okay, because that's what we want to know. Because if it's decreasing, it's going to look like that. So that's the derivative. If it's increasing, it's going to look like that. How do you show that? Oh, come on. Also known as, how can we show that the tangent is increasing or decreasing? Okay, so let's switch it to understanding this by seeing what the tangent is doing. That's what we're saying. So we're going to try to detect these caves down or caves up by looking at the value of the derivative, obviously, and seeing whether it's here f dash x is decreasing or f dash x is increasing. Okay, how do we do it? There it is. Use calculus, obviously. Increasing or decreasing function. Now it's rate of change. Rate of change of a function is its derivative. So we should be able to detect it in that way. Alright, let's have a look at what we're saying here. You remember we started with a Newtonian approach, displacement with time, and looking at the rate of change. But we could put any function here, couldn't we? Any function. And why can't we put, watch this now, why can't we plot the derivative against x? So if we did, what would be the rate of change of the derivative at a point? It'd be the slope of the tangent, so f dash x change implies the slope of the tangent to f dash x. Can we do that? Can we keep applying this rate of change, this calculus approach to any function? Why not? Can you see the idea? Can you see this progression here? We're now interested in how the slope of the tangent is changing. Is it increasing or decreasing? Oh, this is getting multi-layered. Stay with it. So what do we want to do? We want to do the derivative process, or rate of change finding process, to the derivative itself. layer upon layer. We're getting the rate of change of the derivative, because we need to know whether that derivative, that slope of the tangent, is increasing or decreasing to get our concave or concave up or concave down. All right, stay with the idea now. Okay, here we are. If you have a function, you can do it to it and find the slope of the tangent to its graph. And that is also the rate of change of the function. But hey, if we want to do this and get a second derivative, that's the derivative of the first derivative. That's the slope of the tangents to the graph of f dash x, the first derivative. But what we really want from this is the rate of change of the derivative itself, or the rate of change of the slope of the tangent to f dash x, because we're trying to measure what f dash x itself is doing now, because in this region f dash x itself, the derivative is decreasing, and in this region f dash x is increasing. So we need a rate of change measurer. So we'll do it to it. Two dashes, okay, or y double dash, or in the Leibniz notation, do it to dy by dx, d2y by dx squared. Okay, it's not actually squaring x, is it? So here we are, let's come over here. F double dashed x, and here d2y by dx squared for that other notation, or y double dashed, f double dashed. Do you get the idea? This process is unstoppable. If we want to find the rate of change of any function, can we go back up? And we'll just go back up here. Look, we can do anything there. And we can apply this instantaneous rate of change, or the slope of the tangent of the point, to any function. Now, later on in motion problems, we're going to look at the appropriateness of this. How many can you do? You can keep the process going for as long as you like, because we are measuring, here it is, the rate of change of something. And if we're measuring the rate of change of something, we can use the derivative process on it. Okay, so it is an ongoing thing. Now, let's see if we can apply that, because here we said what our problem was if it's concave down, f dash x is decreasing, concave up, f dash x is increasing. So this should be detectable with the rate of change measurer, the derivative of our derivative function here, the slope of our tangent function, or the rate of change of f. Okay, so if f dash x is decreasing, we should be able to detect it with the second derivative. Let's see if we can do that. Okay, to summarise it. What are we doing? Finding the slopes of tangents to the curves, or finding the rate of change of one variable with respect to another. So f dash x measures the rate of change of f of x as x increases, and f double dash x, the next derivative, measures the rate of change of that. And although it hasn't got any obvious graphical implications, we could do the third derivative, measures the rate of change of the second derivative, etc., etc. Now, would we do it in this case? No, we can't see any particular use for this. We're trying to use this one, though, to determine whether some part of the curve is concave up or concave down. Okay, please remember this dichotomy. Here we are looking at something to measure the rate of change of a function, and that is its derivative. Let's read this carefully, finding the rate of change of one variable with respect to another, no matter what that is. Okay, so here it is itself a derivative function. We're going to find the rate of change of that function with respect to x, and always talking about x increasing along the x-axis and looking at the response of or the dependence of the function on that. That function might be itself a derivative. Getting a bit harder to get your head around this. You might have to go back and have a look at some of those graphs again. Okay, can we go on? So let's go back here. Here we are, it's concave down, as we said. The value of the derivative is decreasing because the tangents are going from positive values as x increases to negative values. Anything becoming more negative is said to be decreasing. So what should its rate of change measurer be? The rate of change measurer of something which is decreasing. If it's decreasing, its rate of change should be, have you got it? It should be negative. So in a region like this, concave down, we would say if we find the sine of f dash x, it should be less than 0. What about concave up? Here we're saying we're going from negative slope values as x increases to positive. So the slope of the tangents are increasing. Okay, so what should the rate of change measurer of f dash x give us? Should give us positive values, indicating as x increases, the thing that this is measuring the rate of change of is also increasing. So this is characterized up here by the value of the second derivative in this region should be positive. Okay, can you see it now? This is coming to the end of everything we want to do with curve sketching. You might say, oh, thank goodness for that. But it's good, it's powerful stuff. Okay, let's go down and have a look. Here we are. In simple terms, any derivative is the rate of change measurer of the function of which it is the derivative. That is what we're going to call differential calculus. It is also, according to Newton and Leibniz, it is also the slope of the tangent drawn at that point, isn't it? But it is the rate of change measurer of the function of which it is the derivative. Okay, that's the crux of differential calculus. And we'll put in here, don't forget, we do it by finding the slope of the tangent at any instant. If we want to find the rate of change of any function at that point. Okay, trying to brainwash you a bit here, pushing these two ideas, two interpretations of what differential calculus is all about. Okay, let's keep the journey going here. I hope you hang on in there. Alright, so here we are, points of inflection, talked about before. Now there could be a flattening here. We said that's a stationary point. But there's also another point at which we change from concave or concave down to concave up. We said it was changing curvature. Well, look, here it is here, but there's no flattening. So you can have a point of inflection, that is, a change in curvature or shape, without a flattening. See how this one's coming in, and instead of keeping going concave up, it flattens, and this region is really part of concave down, isn't it? This is concave up, or convex. This is forming a concave down. Okay, so there's a flattening point there. So they are both points of inflection because they are both points at which we have a change in curvature. One with flattening and one more secretive, if you like, somewhere in there. If you try to draw that, let's do it, here we go. We're drawing this now. Somewhere in here, I've got to sort of change my pen, don't I, to swing round? So that's another way of thinking about it. That point is where you have to change the position of your drawing implement, if you like, to swing back up. That's another way of thinking about that point of change of curvature, because in this situation where the graph does not flatten because the derivative is not zero, it's harder to detect that point in that way. Alright, okay, so points of inflection. Here we are, stationary point, there's a flattening, so the derivative will be zero there. okay, and we're going from tangents which have a negative slope through to 0, and they're staying negative. And the gradient is 0 at that point. Okay, here, and you've got your change of curvature because that was part of a cave, concave up, sorry, and this is concave down. Yeah, that's one type. Let's have a look at the other type, non-stationary point of inflection. Okay, so we've got a maximum, local maximum, x equals a point of inflection here, and x equals c. So here, somewhere in here, we have to change from concave down to concave up. Okay, and we want to detect these points at which we have to do that, so we can really nail this function. Okay, so at this particular point, of course, the slope of the tangent is not 0. Okay, so it's not a stationary point. Okay, let's have a look then. Here we are. Now, if there's a point of inflection, then what's going to happen? Well, there's a change of curvature. Okay, so we're going to say it's going from, say, concave down, and this is where f dash x is what? Decreasing. Okay, and so here the second derivative is greater than 0. Oops, hang on, I just got that round the wrong way there. Let's have a look. I'll just go back and do that again. Here, I'll just put more detail in. So here this is positive to 0 to negative. So f dash x is actually decreasing. So the second derivative is negative. Go in a bit more detail there. Second derivative is negative. So on the other one, just recapping that, concave up, negative, 0, positive, f dash x is increasing, so the second derivative will be positive. Okay, alright, so you got that idea there. So we need to find where the second derivative is going to have a sign change, don't we? So what we need to do is to now have a look at a sign diagram for the second derivative. We need to put the second derivative equal to 0 and see what's going to happen there. Okay, so with the second derivative equal to 0, this will be our point of inflection. And if we look at the sign change around that of the second derivative, whether it's positive or negative, then here we have the point of inflection there. Okay, so it's a change in curvature. So generally what we're going to do is put the second derivative equal to 0 to find these points of inflection. Okay, now we're going to go down and check this now. Let's have a look at when we put the second derivative equal to 0, will it always give a point of inflection? Let's take an interesting function, fx equals x to the fourth. First derivative, 4x cubed. Second derivative, 12x squared. And if we put 12x squared equal to 0, we would have this sign diagram. So it actually doesn't change sign there. So there isn't a change in curvature in this one. So we're taking an exception. Why? Because x to the fourth is a flat looking x squared graph. And here it's actually a local minimum. Both the first derivative and the second derivative are equal to 0. So we should check when we put the second derivative equal to 0 that there is a sign change. Okay, and there isn't one here. So this is not a point of inflection. So that's one little exception there. You have to check when you get the second derivative equal to 0 that there is a sign change of the second derivative around that point. So what we're looking for is to make sure that there, this is where the second derivative equals 0, that's going to actually be like this and not be a special case like this one here. Okay, let's have a look at that idea. Here we go. Here's all that we've done so far. Turning points, turning around points. local max, local min, and also in this group, in this set here of orange ones, we've got stationary points of inflection, because these are all stationary points, all flattening points. Now, you can also get points of inflection in the blue set, which are flattening, sure, but some that don't flatten. Okay, these are inflection points. There's the overlapping group, which represent changes of curvature and flattenings. Changes of curvature and flattenings. I wonder if you'd like at this stage to think about this. If the second derivative is naught, what does that mean? Oh, the rate of change of f dash x is naught. Oh, that's what we said was a local maximum, wasn't it? Local max or min of f dash x is when its derivative is naught. Doing the same thing with the derivative as what we did with the original function. Does that make sense? So let's look up here at this one. Can you see that this is the most negative the tangent gets, and then it goes into positive? This is the most negative position. That's a minimum for f dash x. And over here, this is the most positive at this point of inflection. And so this is the maximum value of f dash x. So there's another interesting point. Points of inflection like that are the maximum or minimum values of the slope of the tangent. Because the second derivative is 0, it is the rate of change measure of that slope of the tangent. Oh, interesting, isn't it? Okay, let's keep going and try and build this. Might have to stop and pause the presentation a bit and catch up with that. Okay, so if a curve is concave downwards on interval, its second derivative is negative. We've said that. If it's concave upwards, second derivative is positive. So you have to remember that. Don't know the best way of remembering that. I suppose this is a local maximum. You'd expect it to have big values, positive values, but the second derivative has negative values. Sort of the reverse association. I don't know whether that helps. This is a local minimum, concave up, and yet its derivative is positive. Okay, so I don't know. Somehow try to make your own associations to remember that. Okay, so if the second derivative changes sign at x equals a, the second derivative, then we have a stationary inflection or a non-stationary inflection. Okay, if the derivative is 0 or derivative is not 0, so whether it flattens or not. So that's summarising everything that we have actually done there. All right, how are you going? Are you ready to do some? So let's do this one together. I want you to pause the presentation and try to answer this question, and then I'll come back and do it with you. So what we're doing is looking at various points, and the function, is it positive or negative? So remember, function is positive above the axis, negative below. And then the derivative, which is slope of the tangent, is it positive or negative at that point? And what's the second derivative? Is it positive or negative at that point? Okay, so I want you to pause the presentation now and try to fill this table in, and then we will go through it. Okay, let's go now. So we're looking at point A for a start. The function is positive because it's above the x-axis, correct. The f dash x is the slope of the tangent. It is negative in here. Okay, second derivative, this is what's happening here. The slope of the tangent is what? Increasing, going from negative, or this is part of a concave up, so the second derivative is positive in that region. Okay, what about point B? The function value, it's below the axis, so function value negative. F dash x, slope of tangent would be 0. Second derivative here, it's in part of a concave up, still positive. Second derivative will be positive there because f dash x is increasing. Go to part C. C is above the x-axis, function is positive. The f dash x, slope of the tangent, is going to be positive. F double dash x, it looks like it's a point of inflection. Can't actually say that, but somewhere in here is a point of inflection, so we're going to say that's probably there. It's 0. Part D, it's above the x-axis, so the function is positive. Slope of tangent is 0, there. Second derivative, this is part of, what is this? This is concave down. So this is negative here. Then part E, where's E? Right on the axis, so the function value is 0. Slope of the tangent this way is negative. What are we in there? We're in a concave down, so what we're going to say here is that the second derivative is negative because the first derivative here is changing from positive to 0 to more and more negative. So f dash x is decreasing through this interval here from where it is changed curvature to concave down. It's going to be second derivative is negative. Describe the turning points of y equals f of x. The turning points are B is a local min and D is a local max. Describe the point of inflection y equals f of x. It's a non-stationary point of inflection. We could also say something else. It's going to, let's just scrub this out here, let's draw the tangents in again. So here, getting positive and then getting less, so it's positive. This is a region where the slope of the tangent got its most positive value. So here it's a maximum value of f dash x in that region. Okay, because here that's the maximum value of the slope of the tangent. Most positive it ever gets. So its second derivative was 0, measuring its maximum rate of change. Right, how did you go? Go back and think about all those things, and we're not going to do any more theory on change of curvature or looking at the nature of the derivatives to describe functions. So all you've got to do now is consolidate what we've done. All right, let's go on and do some problems. Okay, here we go. Find and classify all points of inflection. So we're just doing points of inflection now. So here, there's the function, get its derivative, do it again, put equal to 0. Okay, and they don't show this. Put equal to 0, so either x is 0 or x is 2. So this is a sign diagram for the second derivative now. So coming along there, it's going to have a point of inflection here and here because we have these changing sign at those points. So subbing 0 back into the original derivative and into the function, and the same for 2 in the original in the derivative and then into the original function. Okay, so there we have it. We've found this idea here is to see whether they are stationary points of inflection. Are they stationary? Okay, and one of them is this one here. F dash 0 of 0 is 0, so it is a stationary point of inflection. Okay, so it's a horizontal inflection, and that's a non-horizontal inflection. Alright, so that's the idea. You can't tell that from this sine diagram. So you've actually got to go and check, is f dash x equal to naught? Is there a, what could we say, flattening? Is there a flattening of the curve there? So once we've got our two stationary points, we do need 2 points of inflection, second derivative equals naught. We've got to check whether they are flattening points. Okay, so here's a couple for you to do. Have a go. Probably again I'll focus on the more interesting ones there. Alright, let's have a look at the solutions to those now. Okay, question 1A, B. We'll bring up C and D in a minute. I was really doing everything we possibly can with the function now. There's C and D, and E and F. Alright, so I think we've nailed this function. We can tell just about everything about it if we go through carefully. So you might have to rewind the presentation several times and check some of those ideas out. Okay. Alright, here we are. We're going to bring it all together. So we're going to take a function. We're going to find and classify all points where f dash x is naught, so they're stationary points. All points of inflection, increasing, decreasing, convex, concave. Convex is concave up, and concave is concave down. The IB tend to use that notation. Hence gets your graph showing all features. Let's go through the whole thing. So here's our function. We get the derivative, we factorise it, keep factorising it, and then draw a sine diagram. Sine diagram for our derivative. So that's always our starting point. Put -2 on there and 1. Okay, and this is double zero here. X plus 2 squared is x plus 2 by x plus 2, so you get -2 twice. So there's no actual sign change here. When we sub in a value from this region and this region, don't get a sign change, get one here. So we can actually plot this a little bit. Negative, flattening, negative, negative, flattening, positive. Okay, so we've got a horizontal point of inflection at -2, sub it back in the function, function back here to get 19, and we've got a local minimum at 1, and sub that back to get -8. Okay, so we've got the first answer. Let's have a look at any non-stationary points of inflection. Get the second derivative, factorise it, so you got x is naught and -2. Put a sine diagram. This is a sine diagram for the second derivative. So -2, we got that one already. We found that's a horizontal point of inflection. So here, putting in naught, sub it back in the original function. Down here, we get 3 as a non-horizontal point of inflection. Okay. What does that mean? Well, here's our point of inflection here, and in here somewhere, see, that's like a cave down. In here it's turning to a cave up, so that's our function in there, 0, 3, right on the x-axis there, on the y-axis. X is 0. Okay, where is the function decreasing? So we'll go back to our sine diagram back here. Decreasing means f dash x is less than or equal to 0. So it's less than or equal to 1. Okay, all in this region. We'll just rub that out and have a look here. So any region where the derivative is negative, it's decreasing. So it's to the left of 1 and increasing. So this is the sine diagram for the derivative. Increasing when the derivative is positive. So that's greater than or equal to 1. Okay. Concave and convex, so we can either use this or use our graph now. So concave is going to be from -2 to 0, that's part of a cave there, and then concave down, and concave up or convex, x is less than or equal to -2, and over here anywhere from here upwards, because this is our point of inflection. That's where it's changing curvature from this concave down to concave up, sometimes called convex. In the IB, they suggest using concave up and concave down. So that's the biggie, isn't it? That's the big question where we do everything to the function to really understand what's going on. Are you excited? You've actually pulled apart a function and can see why its graph is doing what it's doing, not just bound up by looking out on the calculator. Okay, let's have a look at some problems for you. Again, these are from Hayes, and Harris. So again, we're working with much the same functions. Make sure you do the bigger polynomials or square root ones, and going through all the points of discussion now to actually consolidate that. Okay, and finally, sketching the graph, and you could check with the graphics display calculator. Don't get too dependent on that, because you can't use that in paper 1. Okay, and some extension questions here that you might have a look at. Don't forget the hint here. Important to start with that one. Alright, okay, I'm going to show you the solutions now. Let's have a look. Okay, question 2, part A and B. C and D there. And C. Let's have a look at F. A lot of work in these now. Look at G. And H. Next question there. Don't worry about this. This is just a way of expanding in shorthand notation, not in this course, just multiplying out all the brackets. Let's go down to part B. Okay. Alright, how did you go? Some challenging problems there. Need to talk to teachers and other students about some of those. Okay, let's go on. I've got an interesting final part here. This is a new part of the IB syllabus, very important. Finding the relationship between the graph of the function and the graph of its derivatives. Oh, okay. Let's see if we can do this now. Now, here is the graph of the function. What they're wanting us to do is to draw the graph of its derivatives. Let's take the first derivative for a start. Now, how will we start? Well, we're drawing the graph of y equals f dash x. Okay, so where will we start? Let's draw the tangents here. The tangents here are negative. Okay, so they're going to be, the value is going to be negative. We're going to start off down here somewhere. Okay, why? Because above the x-axis is positive, below the x-axis is negative. Okay, so our tangents have negative values, so they've got to be down here. Excuse me, down the bottom. What's the next interesting point? That's a turning point, so the derivative is 0. So it's got to go through here. Through there. Now, the tangents here are positive after that point, right through to this. So they're going to go up. The values are going to be positive. This is 0. Hang on. So they've got to come down to 0 again. When is the tangent going to be most positive? Point of inflection. Okay, there. Remember, a point of inflection is the maximum or minimum value of the tangents, because its rate of change measure is 0. And then the tangents are negative, so they're going to go below the axis. So that's the graph of the first derivative there. Let's look at the graph of the second derivative. Okay, so we want to do it again to this one. We're going to draw tangents to this one and do the same thing. We're going to draw the graph of f dash x. So let's draw tangents to this one. The tangents here are all positive until we get to that point. So we're going to start up here somewhere with positive tangents. Positive because above the x-axis is positive. Now, there's a stationary point there, so its derivative going to be 0. So that's going to go to there, and then here the tangents get negative. So that's going to look simply like that. It's a straight line. Not very well done. So this is y equals f double dash x. Do you get it? Pretty hard stuff, isn't it? So this is our function, and that looks like a cubic. This is a quadratic, and this is linear. So that's a final check, because in polynomials, when you get the derivative, the degree goes down by 1 on each derivative, doesn't it? So if you've got y equals x cubed, dy by dx is 3x squared. Do it again, and it's 6x. See how cubic with the x to n rule becomes a quadratic, and then linear. Does that line up with your graph here? Yeah, it does pretty much, doesn't it? Right, we've got a cubic looking thing here, and then a quadratic, like a parabola, and then it's linear. Okay. Oh, how did you like that? Okay. Well, have a look, pause the presentation and see what you think. Okay, so let's go down and try another one. Try one here. Alright, so here's another function. Let's try and draw its derivative as well. A bit more complicated. Let's start with drawing tangents down here. Now those tangents have a negative slope, so again we're going to have to start down here with plotting f dash x. Oh, point of inflection here, stationary. So the derivative has to be 0. To be 0 there. Okay, so at that stationary point of inflection, it's going to be a 0 value for our derivative. And then what have we got? We've got still the tangents are negative, aren't they? They still say negative, so it's going to come up, stay negative, okay, and then coming down here, they're still negative, and still oh, how low do they go before they become positive? Okay, so where's the most negative they get? Somewhere there at the point of inflection. Still say negative, but then they come to, hey, this tangent there would be 0. So I've got to be back up here at that point. So I'm going to go like that, and then they keep going positively. Okay, so that's the graph of the first derivative there. Okay, most important idea there. Alright, so what are we doing? Sort of going from plotting the tangents to the 0 positions and so on, aren't we there? Okay, can we do it again? Let's have a look. Let's have a look at the second derivative. Just did a colour change on the pen there. So we now want to treat this function and draw tangents to it. So let's have a look. These are positive tangents, and then that's a 0 position, so we're going to come in positive tangents to here. Okay, then the tangents go negative, down here, and then the maximum negative is there at that point of inflection. Still negative. Now this is a turning point, so that's going to be back up here, 0, and back up there. That would be the second derivative. It looks like we've got a quartic for our blue one, a cubic for a first derivative, and a quadratic. Okay, can you see that idea? We can repeat the process there each time. Okay. Yes, a little bit confusing, but yeah, that's a new part of the syllabus, so hang on in there with that one, and we'll do a few more in a minute later on there. So let's go on now and have a look. Just want to change colour there, there's a little bit of interruption. Let's go on and have a look. So here are my hints to how to do these. Starting on the negative end of the x-axis, determine whether the slope of the tangents are positive or negative. That's what we've been doing. Then start your graph either above or below the x-axis. Start drawing the graph of the derivative. Above if the slopes are positive, below if slopes are negative. When there's a stationary point, the derivative must intersect the x-axis. Whatever that is, the first or second derivative, depending on the function you're working with. So mark those points in, just like I did. And then a non-stationary point of inflection on the graph produces a max or a min turning point on the graph of the derivative. Alright, because a point of inflection there gives you the maximum or minimum value of the slope of the tangent. Alright, so you've got to keep your wits about you. It gets even worse because look down here, I've drawn some derivatives and we've got to go backwards to the graph of the function now. Going backwards from the derivative to the graph of the function. Okay, so let's see if we can do that. This is the derivative. So the slopes of the tangents are above the x-axis, they're positive. So that means I'm starting with a function like this, positive slopes. Oh, derivative is 0. So that's some sort of maximum or minimum. Okay, so let's go like this. Because that's derivative is 0, it's a max there. Then in here, the slopes in all of this region are negative. Okay, so for this next region, up to this point, they have to all be negative. Okay, all negative slopes, and the most negative is there. Okay, because that's the lowest negative value. So what I've got to do is have this coming most negative slope somewhere there. Let's just change that. So I'm going to go like this somewhere. I've got to go to a minimum there. Now this has to be the most negative slope. That's got to be the point of inflection of the original function. And then of course all the tangents go positive. There they are. Up there the tangents go positive after that. Remember, I'm going backwards now. Bit hard. Okay, so same idea, but when this is coming down to negatives here, I've got to check the lowest negative value of that derivative was there. That's got to be my point of inflection. Because remember, the point of inflection is the max or min value of the slope, okay, of the tangent. Okay, are you happy with that? Please note with all this, we are not looking at scales on the axes there, because of course we wouldn't be able to work that out just from shapes of graphs. So we're ignoring scales there. Alright, let's come down to the next one and see if we can do the same thing there. Alright, so what's the first thing that we notice? First thing that we notice is in this region here, this is the derivative, so it's below the axis, the slopes of the tangents are negative. So the function's going to be coming like this, negative tangent, sloping that way. And what's the first thing we notice here? Is the derivative is 0, so that's a turning point. So let's turn it around here somewhere. It doesn't know, you don't know whether it's above or below the axis. We're just mapping it basically on slopes. Okay. So then what have we got? We now have what? We've got a maximum value of the slope there. So let's turn this around, and somewhere there has to be the maximum value of the slope, and then it's 0 here, so it's going to come up, and don't know where. There's got to be a turning point because the derivative is 0 here, and then it goes, the slopes of the tangents are negative, and this is the most negative, so it's got to, oops, hang on, just here, it's got to go, still not as smooth as I like that there. Most negative, so that's the point of inflection. Okay, most negative slope, and then this is 0, so have to just come in here a bit. So here, 0, and then they go positive. So that should be corresponding there. And just get this across a bit, I think. And this is up here. Okay, you get the idea here. Hard to draw, and let's just check the degree. This looks like a cubic, the derivative. So what would have given that? A quartic, power 4, and that looks, with all its turning points there, like a quartic function. Okay, so fairly challenging little bits there to go backwards from the derivative to the original function. All right, do you think you're ready to try some? Let's go down and have a look and see what you think. Draw the graphs of the derivatives of the following functions on the same axes. So we're going to do both derivatives. Okay, let's have a look. Okay, I want you to pause the presentation now and have a go. I want you to draw the graph of the first derivative and the second derivative, and then what I'm going to do is to come back and go through that with you. So have a go there for the moment. Okay, so I'm going to go through it. I hope you've had a go and have drawn your graphs. Okay, so what we're going to do now is draw the graph of the derivative. So we start off over here, and the slopes of the tangents are positive, so the graph will start above the axis. Here is a turning point, so that's going to be a 0 position for the derivative. Then down here we have, that's a point of inflection, that's the most negative it's going to go, and then here's another turning point, so it's going to go there. So let's draw that through. Yeah. Okay, I think I'll just swing it round there. Okay, so we've got that quadratic looking thing there. That's the lowest value of the most negative value of the tangents there, so that's got to be corresponding to that point of inflection there. Okay, get the idea. Now let's put in the second derivative. So this is y equals f dashed x there. Going back after that change of colour, let's put in the second derivative. So the slopes of the tangents of this one are negative, so it's going to start off down here, and then here slope of the tangent is 0 there, so it's got to go through this point, and then the slopes of the tangents are positive. Oh, that's not good. Let's go back up now. Okay, so slope of the tangents here, I'll just try and go through here. So here we go, through there like that. This is now going to be the second derivative. Alright, so yes, it's complicated business, isn't it? We need to check the degree of that perhaps. You're going from a cubic to the red one, the derivative being a quadratic, and then the second derivative being linear. Alright, how did you go? Let's just have a colour change. So let's have a look now at this next one. Let's start here with slopes of the tangents negative through to there. Okay, so coming up here, there's a turning point. So I've got to have a 0 for my function there. A 0 in that position. And then what else have I got? Well, what have we got here? A point of inflection. So that's the most positive the graph gets. It's a little bit crowded in here. It's the most positive. And then what do we got? We have a turning point here down on the axis. So most positive, still positive there. Okay, and we've got it stays at a point of inflection, so it stays positive there. So that's a turning point, but it's still positive. It's a flattening point there. So that's a little bit hard to look at, that one. It's not really very good. We've got to stay positive through here. It's too crowded in this region here to do that very accurately. We've got a couple of points of inflection really in here. It's really a stationary point, not a turning point in there. So there's our quartic going to our cubic. Now the next one should be looking like a quadratic, shouldn't it? So let's have a look at that one. Okay, so now let's do the tangents here. Tangents here, this one are all positive, so we'll start at the top here. Now there is the maximum of the derivative, so that's going to give you a 0 for its derivative. Okay, give you a 0 there, so we're going to come down, and now here the tangents are negative, coming down here, and then we have a, oh yeah, it's too crowded, isn't it? Maximum there, and the turning point of this one is there, so we've got to come around and back up again. So yeah, too crowded in here, because that should be your lowest value there, and then a 0 in there, so it's too crowded like that. Okay, so this is second derivative. Okay, should have made those scales bigger. So that's going to be a quadratic. All right. How are you going? Got to concentrate on these. They're fairly tricky little ones. Let's have a look at this last one now. And we've got, what have we got? I didn't change. Hang on, we'll just change that now. Okay, so here we've got our tangents are positive, so we'll start here. We've got a stationary point of inflection there, so that's 0. Down there. And then how low does it go? Well, it doesn't go under the axis because they're all still positive. So it's going to come around and go like that. Probably should be more symmetrical there. Something like that for our derivative. Okay, just coming straight round like that. Okay, let's have a look at the second derivative. Okay, the second derivative now, slopes of the tangents are negative, so that's going to start off down here. Got a minimum value there, so that's going to be, the second derivative is 0, so it's going to have to go through that point. And then over here the tangents are positive, So it's going to be a linear function like that. All right, quite a bit of work to do all that. We'll get some more practice from Hayes, Hayes and Harris in a minute. Let's go down and have a look at doing some other ones now. Well, here we are. Draw the graphs of the functions given the following graphs of their derivatives using the same axes and no scale. So I want you to pause the presentation and have a go at that. Okay, so we're going backwards here, and let's have a look and see if we can do it. So these are the slopes now of the tangents. So they started off as above the axis positive. So we're doing something like this. Then they went to a maximum value there. Okay, so we'll do that in a minute. But first of all, the derivative was 0. So hang on, I might have to go across a bit. The derivative was 0 here. So they start off negative under the axis, and then here we have a maximum. Okay, so all of these slopes here were negative, and because the function is 0 there, it was a maximum value. So here we're going up all positive to there, sorry. Slopes all positive there above. So we're coming in to this function, to this point here, and then when they went there, they went negative under the axis, slopes negative to there, and the maximum negative was at this point. I'll have to just blow this out a bit. The maximum negative slope was there. Then it was a turning point here, so negative, come anywhere there. Oops, just got to line it up a bit better there. Okay, so here like that, and then the slopes went positive. They went above the axis there. So that should be lined up with that 0 there. Let's just try and get this down there. We're going like that. Okay, so it's going backwards through things. So we have what looks like a cubic here going backwards. A quadratic derivative gave us the original function as being a cubic. How did you go with that? Okay, you can't actually position it with a scale here because of the change in degree of the polynomials. Let's have a look at the next one. Next one's a bit interesting. So let's have a look. Down here, the slopes of the derivative, the slopes of the tangent were negative, so that means the function's going to be coming down like this. Right, negative slopes of the tangents. It was 0. Oh, let's move it across because I've just missed this 0. It was 0 there, which is some sort of a turning point. So let's have it down here somewhere. So we're going down, negative slopes to there. Then they become positive, coming up here. Looks like a point of inflection here. So that's 0, coming up like that. And they stay positive. That looks something like that there. We're just looking at the basic shape there. Okay, so that's that one. That's not too bad. What about the last one here? What do we notice? The graph of the slopes of the tangents under the axis, so they're negative. So coming down like this. There's a 0 for the derivative, which means a turning point up here somewhere. Let's do that. And then for a little time here, the slopes are positive, so it's going that way. And then it's 0 here, the derivative, so that's another turning point. And the maximum value, which should be a point of inflection, is that. See the maximum positive slope there? then it's 0, and then for a little time it's negative, and then it's 0 again. So here that should be the next point of inflection, and then the 0 there, and then it's positive. Okay, you've got to be careful with all this stuff here, particularly these turning points of the derivative, which means this is the minimum slope here. So that's as negative as it gets, and this is the maximum slope of the tangent. Okay, do you get the idea? Fairly challenging stuff, this. All right, let's go and practice some. Let's go and have a look at what Hayes and Harris have got for us. Here we are. Here's the graph of f of x, and they want us to draw the graph of the two derivatives. So let's have a look. So here we are. Let's take the first derivative here, f dash x. As you can see, the slopes of the tangents are negative, so starting from behind there. The function has a turning point, so derivative has to go through the x-axis. It's got a point of inflection, so that's the most the most positive that the slope takes before coming more negative, and then there's a stationary point there, but it stays negative slopes all through there then. Okay, so the same thing. I think the method that we had earlier, the Huddy's hints, works quite well. They're doing it here in notation, but that's what you've got to follow through. The second derivative now, the derivative of the first derivative, well, let's take the slopes of the tangents here are all positive, so you start the graph above, and then we need a minimum value here is this one. Okay, and so you go down, and the turning points here, when the derivative has a turning point, that's a 0 position there and there for the second derivative. Okay, so just check that. It does get messy when you're trying to put them all on the one set of axes, as you can see there. Okay, go through the same points. You can have a look at these points here, but they're trying to put in words, which is a lot harder to read and understand. So you're really tracking it through the slopes of the tangents to the relevant functions. Okay, so here's some here, and I've got the answers coming up there below. So you might draw these on another piece of paper, making it a bit larger than I have and what they've got here. Okay, so pause the presentation, see what you can do with those graphs. Let's have a look at the answers. One part A, and then part B. Part C. Okay, example 18 now. Let's have a look. This is going back the other way. You're given the derivative and you've got to find the graph of the function. So let's see if we can do it now. The derivative here, oops, I won't draw the tangents there. I'll simply say here the derivative here is negative, so it means negative slopes of tangents, so they're coming down. It has a maximum value there, and so they're positives up until there. The derivative is 0 here, so you're coming down to a minimum, okay, in your function, and then you're going to have positive tangents to there, so come to the maximum positive value, which we are not on the same scale, so that should be in that same position there. And then we've got, hang on, no, we've got the wrong position here. I'm trying to do this over here. Maximum positive should be lined up there. So here we've got our local minimum, which is our neg 6. They don't line up. neg 6 there, and then coming through our 0 position. Hang on, got this one. Our 0 position is here. I wish they'd lined up the scales, and then that is our local maximum there. Okay, for our function, which is up here, and then these values are negative slopes coming down. Most negative is there, which should be that point of inflection, and then so on. Yeah, it's a pity these scales don't line up. You can't relate it as easily. They've done a sine diagram, which is okay. I think you should track it through and draw the graph at those various points, remembering that if the derivative is 0 here, here and here, then they are all turning points in between there. Okay, so study that, see what you think. Bit crowded. Let's go and do some. Okay, here are the derivatives. Try and draw an example of a function, and we can't put in scales as such. You could put in the x scale, so you line up those crucial points that I had trouble lining up with the two scales up there, but try and draw it on the same set of axes so that they do match up. Alright, try those two. I'll give you the answers now. There are 2 part A and B. See what you think. The relative positions to the axes in the y direction are not important here. You don't know the scale there, but lining the points up in the x values are important. Okay, let's go on and summarise this. Going back to Pearson's now for their examples. I've left out some. I've left out question 14 here, because that was on motion. I want that to be the subject of a separate presentation. So you can have a go at some more problems here, summarising everything that we've done, and go through to 15 to 24. I think that's the last one. And we'll just go back up because that wasn't good. 15 to 24. I've left out 21 because that was a motion problem as well. I've left that one out. So have a go at those, pause it, and I'll bring up the answers now. Okay, question 1 to 3. Have a look at that. Question 4, 5 and 6. Seven, part of 8. Let's get 8 up there in a minute. There's question 8. Question 9. And question 10. And question 11, we'll have a look at the graph, a bit more detail in a minute. And 12. Thirteen. How are you going? Left out 14, it's a motion problem. Sixteen. There's 17. 18. Have a look at its graph. 19, graph there. $20. That's out 21, that's another motion problem. 22. $23. 24. And its graph. Alright, very busy this presentation, lots to do there. Might want to go back over and check some of the graphs particularly. But you should be feeling pretty powerful now. You can say everything you need about why a graph looks the way it is using calculus, and we're going to go on with a couple of more interesting practical applications of calculus. I think they might be a bit easier to see, so I'd like to catch up with you in a later presentation, but for now it's cheers from me.